Hello again. In this video, we're going to talk about how we evaluate limits that have indeterminate forms of either 1 raised to the infinity, 0 raised to the 0, or infinity raised to the 0 power. I'm going to go over one example where we have one of these indeterminate forms, but the method that we use would be true for any one of the indeterminate forms. Okay, so let's look at this example here. So we want to find this limit, the limit of x raised to the x power as x approaches 0 from the positive side. By the way, this is called a tower function. Anytime you have a function raised to another function like this, that's called a tower function. And this is probably the simplest tower function that you could possibly have. This function is simply x, and the power is also just x. Now, let's see what form this has initially. Of course, you can see that both of these are heading towards 0, right, as x is getting closer to 0 from the positive side. Now, remember, they never reach 0, so it's more like as x gets closer to 0, like maybe 0.01, the power that it's being raised to is the same number. And so this just continues to happen, right? You get closer to 0 for the base, and that same number is the power. And so if you want, you could plug this into your calculator and try to figure out what number you're getting closer to. So that's one possible way of determining this limit. That's kind of a numerical way, or maybe a tabular way, creating a table to find the limit. Okay, we're going to use a more elegant method, more algebraic method. So the first thing you notice is we do have this form of 0 to the 0 power, which is an indeterminate form. If you were to get 1 to the infinity as your indeterminate form, or infinity to the 0 power, you would use the same method in any one of those cases. Okay, so here's the method we're going to use to do this. What we're going to do is we're going to take advantage of a property that we talked about before. If you remember, e raised to the ln of f of x is the same as f of x. And that's because this exponential function with the base of e is the inverse function of this logarithm that has a base of e as well. Remember, natural log has a base of e. And so when you have this sort of situation where you're doing a composition of a function with its inverse, they sort of cancel out and you're just left with the input, in this case f of x. So what we're going to do is we're going to write this x raised to the x power as e raised to the ln of x raised to the x power. Now remember, these cancel out, and so that's just the same as x raised to the x. It's just another way to write that. And we're actually going to find the limit of that function. Now the nice thing about this is, since e is a base that is constant, right, it's fixed, it turns out that to evaluate this limit, you could just simply find what the exponent is getting closer to. After all, the only thing that's changing here is x, right? This x value and this x value. The e is not changing, right? E is a fixed number. So this is equivalent to taking e and raising it to the limit of x to the x, or I'm sorry, limit of ln of x to the x as x approaches 0 from the positive side. Okay, so if I can figure out what this is approaching, right, what this is approaching as x heads towards 0, then whatever that's approaching is going to be the exponent that e is going to be raised to. So it boils down to finding this limit. Now we're going to find this limit on the side, and then come back, and once we figure out what this number is equal to, what this limit is, we'll just put it back in here. So let's focus on finding this limit here. Okay, so one of the nice things about finding this limit is one of the properties of logarithms is we're allowed to pull this exponent in front and multiply it in front of the logarithm. That's the same as x times ln of x. Okay, now let's see if we can evaluate this limit. Well, notice that this is heading towards 0, right? But then this is heading towards negative infinity. Now, if you were to graph ln of x, the graph looks something like this. And notice that as you get closer to 0 from the positive side, the y value continually gets closer and closer to negative infinity, asymptotically, right? This is approaching the x-axis asymptotically, so this y value is just heading towards negative infinity. Okay, so the form that we have currently is 0 times, infinity or negative infinity. And we talked about how we handle these cases in a prior video. What we want to do is try to create division here, which is easy to do because you can just write this as ln of x over 1 over x. Remember, you would flip and multiply this, and that would give you the same thing as this here. So these are equal. We're going to find this limit instead. Now, the reason we're going to find this limit instead is because now that we've created division, now we have, of course, this is heading towards negative infinity still, but this is heading towards positive infinity because x is getting closer and closer to 0, right? So like 1 over 0.1, 1 over 0.01, that's just getting larger and larger. So we now have a form where we can use L'Hopital's rule. Remember, we have to have one of these two forms before we can apply L'Hopital's rule. Okay, so now we can use L'Hopital's rule, right, because we have this form here. And remember, L'Hopital's rule says that this limit is the same as the limit of the derivative of the top one divided by the derivative of the bottom one. Okay, well, what's the derivative of natural log of x? Well, that's just 1 over x. And then we need the derivative of this bottom piece. Now, it's probably best to write that as x to the negative 1 power. It's the same as 1 over x. And then you can use the power rule. So you get negative 1, right? The negative 1 comes down in front. Negative 1 times x and then raised to the negative 2 power, which is the same as negative 1 over x squared. And of course, to simplify this, you would just flip this and multiply by it. And of course, that cancels to negative x. Now we can evaluate this limit. It's pretty clear now that this is heading towards 0, right? X is heading towards 0, so negative x is heading towards 0. All right, now we know what this limit is, right? We figured out this particular limit right here on the side. This is heading towards 0, and that means this is heading towards e to the 0 power. And e to the 0 power is just equal to 1. Okay, so this is a pretty sophisticated way of evaluating this limit. Anytime you have an indeterminate form that looks like one of these, you're going to want to rewrite the function using this little trick here. Instead of f of x, you're going to write it as e raised to the ln of f of x. And you can see what that does for you. It allows you to pull the limit past the e, the base, and you can focus in on finding the limit up here, this power, right? Ultimately, what will be the power for this exponential function. And we did that on the side. And you're going to have to go through L'Hopital's rule to find this limit. So you're going to have to create division somehow. But once you create division, you can use L'Hopital's rule, and then hopefully you can find the limit using L'Hopital's rule. And then you just come back and replace that as your power over here. Okay, so let me just show you real quickly the graph of this tower function, x to the x power. The graph of that function, x to the x, looks like this. And I think you can see from the graph that as x is getting closer to 0 from the positive side, the y value is approaching 1, right, which is what we found it to be algebraically. So the graph confirms that what we found algebraically is correct. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.